Here are our solutions to homework set number 6 for ECE 376. This homework set looks at data collection and doing a chi-square test. Now the first problem is to collect some data. It's your pick what you choose to collect. I'm collecting the voltage across a capacitor. And to do that, I've got this setup. So here's the capacitor going to ground. If I connected 5 volts, the pick will read 5 volts. As I disconnect it, the capacitor discharges, going down to 0 volts. And kind of notice right here, I've got that jumper on there. You got to take that jumper off. If you leave it on, then the pick is initially discharging through a 2.2K resistor through a diode. When the diode turns off, it then switches over to 100K. So trying that again. Charge up to 5 volts. Let it decay. To collect the data, if you go into this program, I can sit there and see the voltage versus time. Send the data to the clipboard. I can copy and paste into MATLAB, then plot the data, and that's how I got this graph right here. That's my MATLAB plot of my voltage versus time. It looks like a nice clean exponential. That's the first part, collect data. Problem 2 is now analyze the data. The data should be decaying exponentially, so if I plot the log of voltage versus time, it should be linear in t. So if I do that, take the data, copy and paste into MATLAB, plot, let's see, do the least squares curve fit. My basis is time and 1. I'm going to curve fit log of t, log of v versus t. Then it says these are the constants. This is your slope right here, and here's your offset. The slope is what I want. Once I know the slope and the offset, I can plot the two data sets together, time versus voltage in blue, and then time versus my curve fit. That's my a e to the minus a to e to the bt, and you can see the two match up really, really well. Yeah, basically it's exponential. Problem 3. Now here's where we get into a chi-square test. I've got a bunch of data. I want to find out, are these two distributions the same? Well, with a chi-square test, what you do is you take the data, you throw it into n bins, and compare the expected frequency versus actual frequency. So for the bins, what I'm going to do is just use the voltage levels. 4 volts, 3 volts, 2 volts, 1 volt. What percentage of the time do I spend in this bin, second bin, third bin, fourth bin? This one should be infinite, so I'm not going to use that. Compare the actual number of data points in each bin versus what I should have. So this is the number of data points above 4 volts, between 3 and 4, between 2 and 3, between 1 and 2 volts. If my data actually decayed exponentially like this, I would spend 1.115 seconds between 4 and 5 volts, 2.554 seconds between 3 and 4 volts, and so on. That gives me my probability. So here's the region. Here's the time I spend in the region. The probability is what is 1.115 over the total time? 13%, 17, 25, and so on. Take the number of data points that you have, multiply by p, that's n times p. Here's the actual data. Now comparing, to do the chi-square test, I take the difference squared divided by np, difference squared divided by np, add them all up, I get a chi-squared score of 0.2251. If we go to StatTrack, I can convert the chi-squared score to a probability. I've got 4 bins, meaning 3 degrees of freedom. Chi-squared score is 0.2251. The probability then is 2.7%. So basically, this is an exponential distribution. Now, a couple people in the homework, they didn't take the LED resistor out, so the data look like this. And what you wind up with is a very high chi-squared score. That's kind of what you expect. This is not a simple exponential decay, and it shows up in the data. Take out that resistor, and you have a nice clean exponential. It is exponential. Okay, so that's the first 3 problems. Problem 4 looks at This problem looks at generating a six-sided die. Is it a fair die or a loaded die? So what I'm going to do is wait till I hit a button. When I press the button and release, the time that I held the button down determines the die roll. I basically count really fast, mod 6. Whatever the value is when I let up is the die roll. So for example, here's my six-sided die. I go press, release. I just rolled a 1, 6, 6, 4, 1. This is also sending the data to the serial port. So I can see over here, let's clear the data. When I press the die, I'm getting the numbers. Copy that to the clipboard, send it to MATLAB. I can analyze the data. So when I do that, I roll the dice a bunch of times and count how many times I got a 1, 2, 3, 4, 5, and 6. To do a chi-squared test, I compare the actual data versus what it should be. If this is a fair die, the probability of each number is 1 in 6. Based upon how many times I rolled it, here's how many times I should get a 1, 2, 3, 4, 5, 6. Take the difference squared, divided by expected value, gives you the chi-squared score. Add them all up, I get a number. To convert that to a probability, I go to StatTrack, or chi-squared table. I've got 6 bins, meaning 5 degrees of freedom. My chi-squared score is 9.32. The probability is 90%. So I'm 90% certain this is not a fair die. And it could be just I got unlucky. It could be this code actually is biased. For example, when I count mod 6, I might say 1, 2, 3, 4, 5, 6. If I get to 6, go back to 0. That extra time I spend on the number 6 might mean that I'm spending more time there. I've got a higher likelihood of releasing the button during that time. Based upon my data, it looks like the die might be actually loaded. I'm getting too many 1s. Actually, not enough 1s. And your results are going to vary. It is random. Problem 5 says, suppose I change the code. I set it up so 9% of the time I always get a 6. The rest of the time it's a fair die. Can I detect that the die is loaded? Well, again, if I have the source code, I can look at it and say, yep, it's a loaded die. If I don't have access to the source code, what I can do is collect some data, roll a bunch of numbers, and then compare the actual data versus expected. In this case, I got a chi-squared score of 19.8. Going to StatTrack corresponds to a probability of 0.999. So with the chi-squared test, I can tell that, yep, I am getting too many 6s. This is a loaded die with a probability of 0.999. Problem 6. Now this is kind of a fun one. This is trying to find out, are you really psychic? Well, the pickboard can roll a 4-sided die. And I'm going to push a button over here. Do I think the die roll is going to be a 3, or a 1, or a 2, or a 0? I'm going to guess what the answer is, roll the die, and see if I'm right. So this is the same code we had before, but instead of checking port B pin 0, I'm going to check is any pin on port B pushed. Wait until I hit any button. That changes port B from 0 to some other binary number. While the button's being pushed, I'm going to roll the dice really fast, counting mod 3, and keep track of which button I pushed. When I release the button, I know what X is, I know what button I pushed. If the two match up, I guessed the right number. Otherwise, I was wrong. And display how many times I'm right, how many times I'm wrong. So this is what that looks like. I'm going to think the first number is going to be a 2. Press, release. And I was wrong. 0. Nope. 3. Nope. 1. Hey, you got it right. 2, 3, 1, 2, 1, 3, 0, 3, 1, 2. So I was right 4 times, wrong 10 times. It's kind of a quick way to automatically collect the data. So that was the first part of the homework. Write a program that records what number you guessed and compares it to what the actual random number is. Do the two match up. So I did that, collected some data. I was right 14 times, wrong 31 times. What does that mean? Well, that's a chi-square test. I should be right 1/4 of the time. There's 4 numbers. Wrong 3/4 of the time. Based upon the number of rolls, I should be right this many times, wrong that many times. I'm actually 14 and 31. To calculate the chi-squared score, same procedure. Take the difference squared divided by NP, difference squared divided by NP, add them all up. I get a chi-squared score of 0.8963. To convert that to a probability, go to StatTrack. I've got 2 bins, meaning 1 degree freedom. My chi-squared value is 0.89, corresponds to a probability of 0.65. So from this data, there's a 65% chance that I'm not just guessing. Numbers like that are usually, well, that's just random data. If I get something like 0.99, 0.98, I could be pretty sure I'm not just guessing. If it's really, really low, maybe I fudge the data. This is basically no conclusion. So sadly, apparently I'm not psychic, but you probably already knew that. Anyway, that's homework set number 6 for ECE 376.